All right, good morning and good afternoon, everyone. Thank you for attending our product webinar, the new Fiddler for Unstructured Models in Advanced XAI. So a few reminders and housekeeping items. This will be a demo-driven webinar, and after the webinar, you'll get a link to the recording via email. We send that out. And throughout the webinar, please submit any questions, upvote any questions in the Q&A box below, and we'll answer those questions at the end. All right, so today's Fiddler speakers will be Sri Kamireddy, the Director of Product Management, Sabina Cartasio, Senior Product Manager, and Josh Rubin, Senior Manager of Data Science. And in today's agenda, Sri will cover the Fiddler overview, and Sabina will walk through the product updates, the new homepage, class imbalance, and so forth, and we'll be showing demos as well. And at the end of the webinar, we'll answer the Q&A section. Now let's turn it over to Sri.
Good morning, folks. Let's start with how Fiddler helps make a difference. We help you, the model developers, build and maintain better and responsible AI models. And in turn, the society benefits because of the launch of this fair and trustworthy AI. Our goal is to operationalize AI ML in a safe, trustworthy way and reduce your time to value using AI. This is achieved through 4 pillars of Fiddler. There is monitoring, explainability, analytics, and fairness. Continuous monitoring helps proactively detect model issues like drift or performance issues. Explainability provides granular explanations for all predictions made by the model. Analytics allows you to dig deeper into the models, evaluate your models, and perform root cause analysis. Fairness detects bias both in your training as well as production data sets, helping you build equitable models. Fiddler drives 3 positive business outcomes. Monitoring functionality of Fiddler helps accelerate AI time to value and scale by helping you deploy models confidently to production. Explainability and fairness enables you to build trusted AI solutions. Analytics functionality helps you improve quality of predictions. And overall, Fiddler helps bring organizational alignment all the way from data scientists to C-suite. Let us quickly look at the demo of current Fiddler functionality, and then we will go look at all the new functionality that Sabina will be demoing.
Let's look at how Fiddler supports the 4 pillars of monitoring, explainability, analytics, and fairness. Let's jump into a model that is getting production data published to it. So I am in a particular model, and what you see in this model is that this blue line, which is the drift, was pretty flat for a long period of time, but recently the drift started increasing. So at this point, you would want to know what is causing the drift to this prediction, which is the probability of the loan status. What you see here is that there is a particular feature that is causing a lot of prediction drift impact. This particular feature is drifting, and this feature has a certain amount of importance. As a result, this is causing a significant impact to the prediction. So if you go back to a previous time, you see that that particular feature is not causing the drift impact at all. So if you come back here, you can actually look at what's happening in that slice. You see that point in time, you see that prediction and production and baseline data are deviating. The baseline data had a lot of data between 0 to 100K for this particular feature, which is total balance of existing mortgage, but nothing much elsewhere. But the production data is clearly drifted because there's a lot of data between 200,000 to 300,000 and less data between 0 to 100,000. And if you go back to a previous point in time when there was no drift, you see that the production data and the baseline data are pretty similar. So now that you know where the which slice of data is a problem because we detected drift, we also know the feature that is contributing to the drift. You can do further analysis. So here is you can just click export and you can do analytics now. You are seeing monitoring before. Now you can do analytics. Let's say there are multiple different charts you can do. What I want to do first is I want to do slice eval. So I want to do evaluation on that particular slice. When I do the slice eval on that particular slice, you see that the data, the model is performing really poorly. The positive, which should be high, negative, which should be high, but that is actually not high. You are seeing that the predictions, when the predictions are negative, the actuals are positive. So that is not that box should be much lower, but that box is much higher. So there is a really big problem for this slice with this model. So now you can also see what might be happening with comparing this slice to the full data set. When I do feature impact, it is going to run through the entire data set and it will come back with what is the feature that is causing the highest impact in this particular slice. And you see the total balance of existing mortgage is 23%, whereas the entire data set, that feature impact is only 11%. And now essentially it's clear that the data is drifting and this is the feature that is causing the drift. And you also saw that the model is performing very poorly on this slice of data. And if the drift continues like this, the model is not going to continue to perform, which will cause production issues for you. So we can also explain. So what I clicked here is you can jump to a particular prediction point, and you can make changes. Here you see that the total balance of existing mortgage is 227,000. Maybe I'll change it to 60,000, which is in line to most amount of data that you see in the baseline data sets. Now I rerun it. You see that the predictions have changed, and you see that is not that important anymore. It actually is not at all important because it's potentially in line to what we were seeing from the model before. Essentially, you can do all kinds of what if on these data points to see how these data points are impacting your model predictions. So we looked at monitoring, we looked at analytics, we looked at explainability. Now let's jump into a quick demo of fairness. So here is a model that is predicting credit approval, and it has several different feature inputs, and there are two feature inputs that are considered protected in this particular model. There is gender and race. So when I do gender and I want to see how the favorable outcome for this protected attribute is, jumping to fairness metrics. Let's see one particular metric in the interest of time. You see that male and female, they have similar group benefits, which you can see as a benefit where the two groups are treated equally, right? So looks like the two groups are treated equally. Let's say we do compare on race. And race too, there seems to be slight differences, but they seem to be doing okay. What if the input features are both race and gender, right? In this case, now I do race and gender together as protected attributes. And what you see here is that there's a big difference. There is this one group that has a lot of group benefit compared to another group. So there is clearly groups are not being treated equally. This calls for you to do deeper analysis to figure out why the bias might have crept into your data sets and models. So that's a quick demo of the 4 pillars of monitoring, explainability, analytics, and fairness.
As customers onboarded and brought production use cases and production loads, we found several areas for delighting the customers. First, as the customers brought tons of models into the platform, they needed a single pane of glass to monitor all their models. And also there were different types of models that needed monitoring, like imbalance data sets, models built on imbalance data sets, monitoring unstructured data like computer vision and text NLP. Sabina will walk us through all of these updates next.
Thanks so much, Sri and Karen as well. So as mentioned, I'll be covering a brief overview of some of the new features that we've shipped here at Fiddler AI. We're also going to dive a little deeper, leveraging some demos at the end of the slides. So on more of the user interface and experience side of things, we've launched a massive revamp of the Fiddler homepage. With this revamp, we're introducing our single pane of glass homepage, which allows users to view information for models across all of their projects. Alongside detailed monitoring information, we also display a job status tracker. This really enables you to keep track of long-running async jobs. And we're actually going to play around with this in just a second, but first, let's move on to our next feature. Great. So next, we're going to talk about monitoring rare drift. In reality, this is Fiddler's solution to class imbalance. So class imbalance specifically applies to classification problems, and this refers to data samples from one or more classes that significantly outnumber the samples from the rest of the classes in the data set. So real-world applications where class imbalance happens includes fraud detection, medical diagnoses, and so many other fields, even facial recognition, right? We see this when we try to unlock our phones with Face ID. In reality, there are only a few instances of our face, but many samples of faces that are not ours and should not successfully unlock our phone. So without a proper solution to monitoring drift in cases where class imbalance is present, there's really no way to detect dramatic drifts and changes from the baseline data that you use to train your model and what you're witnessing in production data. So we've released a solution centered around global and event-based weights to address this common problem. You can kind of see on the right-hand side before the solution, if you brought in balanced data sets, that it's more flat, and on the bottom, you can start to see that drift occurring. So we're actually going to dive much deeper into this during the demo, but let's go ahead and move on for now. So our next functionality that we can take a look at is our vector monitoring solution. This new functionality really allows users who are working with natural language processing, NLP, or computer vision CV scenarios to effectively monitor their data. Data for these scenarios is also referred to as unstructured data. Now, it's very hard to tell when unstructured data is different from when you first used it to build your model. This really leaves you wondering if the decisions your model is making in the production environment are correct. For unstructured data, we leverage vectors or embeddings. These are internal representations of what the models learn. This can be text or images, and these are passed into Fiddler. Fiddler then leverages a cluster-based binning algorithm to easily allow users to visualize drift between the baseline and production data. You can also view other information like how the data is shifting over time. You can drill down to different dimensions impacting the drift, and we'll go into a lot more depth during the demo. Let's go on to our next feature for now. Great. So the last feature that we have to cover before we jump into demos is our flexible APIs. In short, these are decoupled API calls that empower users to leverage Fiddler for their specific needs. So what do I mean by that? First off, every user will create a project. In essence, this is a namespace that will house all of your models. If a user only has a need to monitor on Fiddler, then they go ahead and upload their data set, set up a model for monitoring with minimal friction, and then they just publish events to monitor. Now, if a user was instead interested in explainable AI, then they could choose to add a model artifact or a surrogate. to produce the explanations. In summary, this additional flexibility enables you to use Fiddler in the way that's most valuable to you with minimal effort. And that was the end of our overview slides. With all that said, let's move on to our demos. We'll start with a demo of our homepage, then our solution to class imbalance, and end strong with a demo of our vector monitoring capabilities. So let's move on to our UI to get started. So taking a look at Fiddler's single pane of glass homepage, we have a variety of information pertaining to our model monitoring capabilities, alerts, as well as our async jobs. First and foremost, we see 3 visualizations at the top of the page that give us a high-level overview of how many alerts have been triggered across the different alert types we offer in specific performance, data drift, and data integrity alerts. Performance and data drift alerts are defined by the user and based on a specified metric and threshold or value. Data integrity alerts, such as the number of missing values, can also be customized and defined by the user. Directly to the right of these 3 donuts, we have our recent job status card. This is especially useful in enabling users to keep track of long-running async jobs. Certain jobs like publishing production events to monitor or uploading a dataset to the Fiddler platform can take significant time depending on the scale of the incoming information. The recent job status card gives us a single view to track our jobs and check whether they are in progress, failed, or whether they've completed successfully. We can navigate from the recent job status view to a created asset upon completion. So for example, in this first row, we can see that the dataset has successfully been uploaded. We can click on this link to view more information about the dataset itself. Now let's go back to our homepage. Directly below these 4 cards, we have our monitoring summary table. This table displays our models across all of our projects, alongside with the associated traffic, drift, which is calculated using JSD, and the number of triggered alerts associated to that model. This view gives our entire team a method of visualizing monitoring information. Not only does this view offer a consistent experience across users, it also makes it much more seamless for you to get from your model to your monitoring charts. And we can do this right here. So clicking on the monitoring charts, we can now diagnose a variety of different metrics and issues. So we can see here every data point that triggered one of our alerts. So we've covered the different components of the single pane of glass homepage for Fiddler AI, which gives us a breakdown of triggered alerts for each alert type, a seamless view of our async jobs, and finally, a table view of our models across all of our projects. So let's quickly go back to our deck for the next demo. I want to briefly walk through Fiddler's solution to class imbalance data monitoring. So taking a step back, we can imagine that we're working with a fraud model, for example, to predict fraudulent credit card transactions. And hopefully when we think back to our own experiences with fraudulent card transactions, they are few and far between. A common theme with fraud models is imbalanced class distribution. This means that there are many more negatively labeled samples than positively labeled samples. In the case of our credit card fraud scenario, this would correspond to when there are very few cases of fraud amongst many non-fraudulent transactions. Now, let's say that we have an unexpected surge in fraudulent behavior in production. In this example, we can see that the number of high probability predictions has increased 20 times when we compare it to the predictions made on the baseline data. Without making any changes to the way that drift is calculated, we actually won't pick up on the substantial change in fraudulent activity. This is because drift calculation looks at the prediction distribution as a whole. In the grand scheme of things, there's not much change in the overall distribution of things. So let's actually go ahead and look over at the UI monitoring experience to see this for ourselves. So coming over to the UI, we can see our drift versus average value monitoring chart. If we hover over the different data points, we can see the drift value, the average value, and the traffic count. Directly below, we see our different features as well as a column that dictates the feature drift. Opening up one of these features, we also get a feature distribution. Now, looking at our monitoring chart, our feature drift value, and our feature distribution chart, we really don't see anything that would raise a red flag, letting me know that there was a surge in fraudulent activity. So let's talk a little bit about how Fiddler's solution works. Fiddler's solution relies on a weighting system. This solution allows users to set either global or local weights. Global class weights would upweight the events from the minority class so that the resulting histogram can capture changes in the prediction drift effectively. Or users can provide event level weights if they require more granular control of weighting. We can see here that global weights are applied to our classes. Now let's see what our monitoring charts look like. Great. So in the model monitoring chart, we can clearly see the drift caused by the surge in fraudulent events. Even looking at the feature drift and the feature distribution, this surge is even more obvious. So with our class weight set, we can confidently monitor our fraud model and be ready if there's a large increase in fraud. Now let's go back to our deck for our next demo. I want to talk about vector monitoring, but first let's do a quick recap of creating word embeddings from scratch. Now let's say that we have the concept of a cat. Everything we know about a cat thrown down on the screen as shown here. However, cats really don't exist in the world by themselves. They exist in relation to other things, like dogs, for example. And dogs are different from cats. So let's say they go somewhere on the other side of cats. And let's add a little bit of context. We're going to say that cats are more cat-like and dogs are less cat-like, and that's why they're further away. Now, if we look at this chart, we can see that cat and dog are 4 units apart from each other. So let's visualize this and write this up as a pandas data frame. So looking here, our pandas data frame, we can see that we have our cat, dog, and the attributed cat points. Our cat gets 4 cat points, and our dog gets 0 cat points because it is, less cat-like. Now, let's go ahead and consider more animals to really drive home this idea. So we're going to add lions. And lions are pretty cat-like, but they're bigger and stronger. So let's say we put them to the left or a few points lower than cats, but definitely not as far over as dogs. So we can see here that the cat is still attributed its 4 points, but the lion has 3.5, slightly to the left of the cat. And now let's say that we add a wolf. A wolf is definitely much closer to a dog than a cat, but it's also a lot more intimidating than a dog. So let's put the wolf further away than the dog is, right? So we can see here that the wolf has negative 0.5 points, cat points, and the dog still has 0. Now, there's still some open questions like, why are wolves and lions separated by dogs? Like, how does that make any sense, right? Sure, lions and cats are both felines and wolves and dogs are both canines, but let's think about it. Cats and dogs are very domesticated and wolves and lions are very wild. So if we're teaching a computer to only consider the dimension of cat-likeness, hey, this is like a cat, or hey, this is less like a cat, it's really not going to learn anything important. This is the nuance of our human experience that computers are missing out on. So let's teach our computer this nuance by giving our graph a brand new axis, wild or domesticated. As you can see here, this will be called more wild. Now we start to see that wild animals can be grouped above and domesticated animals can be grouped below, but still close to their feline or canine counterparts. Now let's take this idea and continue to expand it into more and more dimensions. Is this word about houses? Is it about fish or space and so on? That's what word embeddings are. Word embeddings in specific are when words or phrases from the vocabulary are mapped to vectors of real numbers, like the table you see below. You'll hear me refer to an embedding technique called word to vector in this demo. This quite literally translates to word to vector. And note that vectors can come from text or image data. Now, I alluded to this, but I just want to drive this home. One very important feature of word embeddings is that similar words such as dog and cat, which are both pets, would have a smaller distance between them than words that have little to no semantic relationship, like dogs and astronomy. So now that we have a better understanding of how to create word embeddings, let's take a look at an example of vector monitoring. So in this example, we're going to use an NLP based example, specifically looking at text from a variety of different news groups. In our specific example, we're going to look at text data from a variety of topics, including technology, sports, automobiles, science, and more. So let's say that our baseline dataset uses text from a wide variety of groups, like the ones I just mentioned. And here you can see that I have groups such as, auto, the different groups, and then you can see an example of what this text looks like. Now, if I were to go ahead and generate a word cloud based on all of this text, I can see that certain words bubble up, and these are the themes or trends. And I can see things like sports, words like games, or technology with words like source code or hard drive. However, over time, the meaning of text can change, and some of the common words and trends that we identified before, like games, like hard drive, and source code, are no longer present. Now we see a trend amongst words like theory, universe, space. So how do we detect this change on Fiddler's platform? Let's actually head over to the UI and check this out. So we're back at our monitoring UI that we've seen before. And before I get started on talking about vector monitoring drift, let's talk a little bit about how to define a vector on Fiddler. So we have a number of different features at the bottom here. You'll see F250, F185, etc. So users will actually bring in all of these features and group them to create our vector. So it's very similar to the example that we were following when we were learning about how to create embeddings. So once the user has grouped their features and created their vector, they can also assign a number of clusters. In this case, there are 5 clusters assigned to our vector 1. And if I go ahead and expand this vector to view the feature distribution, I can see the 5 clusters defined. Now, what this is telling me is that as I look at every single cluster, I can see that the production and baseline data are about the same, no matter what cluster I focus on. This is to tell us that there's little to no change in the drift of our text. Now, let's click on the next data point in our monitoring chart. Now I can see that the drift value has increased, and I can also see that in clusters 1, 3, and 5, the production and baseline are quite different. And now we can start to see that drift. Now let's click on the third and last data point in our monitoring chart. Now this one has the most substantial drift, and we can really see it amongst clusters 1, 3, and even 2. And what you'll notice is that none of the clusters completely disappear. This is because we've used Word2Vec, as I mentioned, to create the embeddings used. However, Word2Vec creates embeddings for individual words in a sentence. And there are general words that can be used across any topic or domain. If we had leveraged more sophisticated embedding methods to maybe consider, whole sentence or context, it's possible that we would see even more clear changes. Now let's head over to our deck really quickly. Another helpful way to visualize drift for our vectors is by leveraging UMAPs. UMAP stands for Uniform Manifold Approximation and Projection, which is a mouthful to say the least. But UMAP constructs a high-dimensional graph representation of the data and then optimizes a low-dimensional graph, as the one we see above. This visualization allows us to more easily identify changes in patterns. So we can see on the right-hand side that the heavily focused or science-focused group in the production data is displayed in green, and it's clustered together, again, because we said that vectors with semantic relationships would kind of be closer in distance, and it's mapped against the baseline data. So this is a feature that will be coming to Fiddler in the very near future, but for now, users who have access to the Fiddler platform can leverage a demo notebook to run this experiment themselves and dig a little further into our vector monitoring solution.
Thank you, Sabina, for the product updates. So before we start with the Q&A section, I'd like to go over the resources that we have really quickly. We have in-depth white papers on how Fiddler addresses class imbalance, how to measure model drift, and also a few data sheets as well that we include the links over the chat so you can download them and read further on. So let's start with some of the Q&A questions that we have here. So one of the questions that we have here is, how is the cluster-based binning algorithm different from Euclidean or cosine distance for vector monitoring? Shri or Josh, would you like to answer that?
Yeah, so the cluster-based binning algorithms essentially provide more actionable insight on how the data changed over time. It basically helps us accelerate the time to find data drift and identify which features contributed to the drift.
Okay.
And maybe I'll just throw in a couple thoughts too. So, purely using something like cosine distance on all of your data treats it as a blob, right? And so essentially the innovation here is that this clustering method partitions the data in the high dimensional space. So, data in these vector representations is often high dimensional and often intricate and contoured in the multidimensional space. So by carving that up using a clustering method, it's essentially a sort of low resolution density estimate for how that data resides in the high dimensional space. So in terms of measuring drift one way versus the other, this should give you a higher fidelity representation of how data may be moving. You're averaging over fewer dimensions. It'll also shortly lead us to being able to do some really sweet things like multivariate, a principled multivariate outlier detection. So yeah, think about having a sort of a nuanced high dimensional description of where the data lies and being able to measure with respect to that rather than lumping it all into one blob.
Mm-hmm. Just to follow up on the embeddings and vector monitoring, can Fiddler ingest embeddings from a DNN?
Yeah.
Okay. And
yeah, yes, the final vector can come from anywhere. If the vectors are meaningful, we'll be able to better detect the drift. If I think that's all it matters. Meaningful vectors, meaningful embeddings.
Okay.
We do also have this notion of metadata fields that are not necessarily model inputs. And so, you may have a model that ingests an image or a piece of text, but you may also want to assign intermediate stage embeddings from your model that you wouldn't consider to be proper inputs. Those can be defined as metadata columns. And then you can create this custom vector monitoring instrument based on those.
Okay. And we've got another question on word embeddings. Is there sparse and dense representations for word embeddings? Can you tell us a bit more about them?
That's a fantastic question. So, it's not an uncommon thing to do for users to do something like, the time-honored term frequency, TF-IDF vectors, and those are notorious for creating large sparse representations. So, there may be, if you have n-grams, if you have bigrams and trigrams, you can end up with a vector space that's 1 million dimensions. And usually a particular piece of text only has a few of those. And so you'd like to be able to just sort of include the non-zero ones. So today we support dense vectors only. But very shortly, you'll have the ability to include something like a dictionary encoded in a single input column that allows you to represent a sparse vector. So it's very clearly on our short-term improvements for this feature. Super important.
And to follow up on more of the word embeddings, there was a question also Fiddler and attention/transform models and word embeddings. Can you weave a thread and relate these?
Fiddler.
So yeah, I think our, Word2Vec gives you a fairly, simple onboarding for language if you've got it. And a deep learning model or not a deep learning model, I think we've provided the capabilities so that you can bring your own embeddings from your own model or from a sophisticated model like a big transformer model and include those. And in fact, we've had a lot of success monitoring simultaneous multiple representations of the same model. Sometimes you get something like an early warning if you use upstream layers. Now, the degree of weaving the thread, and solving the, the diagnostic problem of like, how does this particular representation, how does drift in this particular representation correspond to something that's actionable? I think the answer to that is, using this binning, you'll be able to identify, this kind of cluster-based binning, you'll be able to identify, where migration has happened in that high dimensional representation. And then using something like UMAP should allow you, even in that scenario, to isolate particular examples that are indicative of the kind of drift you're seeing. So I think, in the first cuts, I think that's how we're seeing the diagnostic process working. And as far as I can tell, that should be totally valid also for, complex embeddings that come out of big, sophisticated models.
Okay. There is another question on the vector monitoring. How do you know the clustering method is effective? Is the user the one who decides the method, or is the platform?
I'm happy to keep going until people get bored of me, and then we can somebody else can go. Yeah, so the underlying mechanism we built will ultimately make it possible to use different mechanisms, but than just this sort of simple clustering mechanism. But this is sort of simple and powerful. So I think calling it clustering is a little bit of a little bit misleading. So we do use, under the hood, it's using clustering methods, but that's only important in that we're using those methods to partition the high dimensional space. So even if your data is not clustered, even if it conforms to some huge smear in the high dimensional space, clustering will still subdivide that into bins. And then you can track migration between bins as drift. And that's the important piece. So as long as you have a sufficient population in each of those bins, then you've done a good enough job of dividing up that high dimensional space. That's the key thing. So, when we run the binning, we're running checks to ensure that the bins that the clustering, these partitions that are created in the high dimensional space are, sufficiently populated. That's the key characteristic.
All right, so let me, there are a lot of questions on the clusters. So am I understanding it correctly that we first cluster, then apply drift analysis within each cluster, and based on the selected embedding dimensions, which we treat as features for JSD?
I'm not sure I fully grokked that. I think that the procedure works like this. You provide vectors. I think you also are able to set a number of bins or clusters that you'd like to use. On the back end, we run clustering to create partitions in that high dimensional space. And those work like regular histogram bins. So if you pick 10, you have a fairly, you have a 10 bin density representation of where your reference data resides. That same binning transformation gets used subsequently on production data that comes in. So we monitor 1/5 of your data ended up in this bin and 10% ended up in this bin. And we look for changes between the production data and the reference data according to the same partitions. So you're not providing the bins or the clusters. That's something that's computed, by the platform after you've submitted your reference data during the sketching procedure.
Okay. There's another question on word embeddings. Can you tell us a bit more about word embeddings in the context of sentences, paragraphs, and how the same sentence with a different context simplistically when placed between different set of sentences could impact the monitoring?
Yes, a lot of exciting questions on unstructured and embeddings. So essentially, you are going to vectorize, and when you use the right vectorization technique, irrespective of what the sentences are, if the sentences mean similar things, the vectorization should be similar for these sentences that mean similar things. And those vectors essentially, once input into the platform, we can then monitor if the meaning is drifting, right? That is essentially what we are doing. We found that monitoring individual components of a vector are not useful. What is useful for our customers is monitoring when the meaning starts drifting, right? So you provide us meaningful vectors, and we will make sure to detect drift when the meaning starts drifting.
Okay, more on vectors. So what size of feature vector can Fiddler handle? And can it provide any analysis on the ingested vector, like feature importance?
So I guess I'll jump in here. In the first cut, I believe that, so individual components, as I said before, will very shortly be moving from kind of column-wise components to something that allows you to embed larger vectors as its own kind of data type in a single column. So right now, the number of components of the vectors is constrained by whatever the limit is on input columns. I think it's in the low numbers of thousands today based on our database backend, but I'm not quite sure what that exact number is. You know, it's sufficient to support embeddings that come out of most of the big language models. And then, of course, subsequently, we'll be able to serialize larger vectors or sparse vectors into single columns. And then there will be, you know, essentially no limitation. I can't speak to whether there are performance implications to having enormously large vectors. So there may be some constraints placed on that in order to preserve platform performance. But you know, I think the goal is to have, you know, any sort of sensible use case covered in that solution.
Okay, so this question is, can views be cut across metadata elements that are not included in model features?
Can views be cut across? I'm not sure I understand if Josh or Sabina understood the question.
So if we're talking about the analytics and fairness examples, I think we can use metadata columns for creating segments to analyze. I don't think there's any restriction that prevents us from looking at that. So, I mean, part of what makes fairness work is the ability to segment according to protected classes that are not model inputs. Like you might not have gender as an input to your model, but you want to split your data up that way for the fairness analysis. So yeah, the analytics tools should allow you to segment across metadata if that's my understanding of the question.
Okay. The next question we have is, do you support tensors?
Yeah, that's an interesting question. I think in the existing clustering algorithm, you know, the recommended procedure is to flatten them and let the clustering algorithm pull out the most meaningful ways to partition that. If it becomes a common pattern and somehow the existing procedure is insufficient, you know, we should be baking in the infrastructure to do something more sophisticated there. But as of yet, you know, it's kind of neither. We haven't heard it enough yet, nor do we have the data that you know, flattening those into you know, one-dimensional vectors doesn't solve customer problems. So we just need to collect a little more data.
Right. But the next solution of sparse enabling capturing of these sparse vectors is it would enable a lot more functionality, and at that point, if we see tensors are needed, we can easily extend it. We pretty much built a flexible platform.
There's a question on high class imbalance. So could I apply models with high class imbalance other than identifying malicious behavior? Can you provide some use cases?
Yeah, so high class imbalance. So in all my previous experiences where I had used machine learning and artificial intelligence, a lot of times high class imbalance is the primary use case. I did help build predictive maintenance models for an industrial company, and predictive maintenance. Your devices like windmills break once in a while. After a really long period of time, the IoT data is coming, and once in a blue moon it breaks. It's highly, massively imbalanced, right? I also worked in where the disease happens for 1 in 100 people or 1 in 1,000 people. So again, massive imbalance. In a lot of ways, I see imbalanced data sets as being as one of the primary use cases in machine learning.
All right, there's a question. What makes this solution different from other model monitoring tools out there?
Great question. So in terms of Fiddler, our goal is to help you build trustworthy AI solutions, and we are not providing you a point monitoring solution. We are providing you all the necessary tools for you to go build a trustworthy AI solution. What do I mean by that? If our solution was just monitoring, you'd be able to monitor and maybe detect drift and maybe detect performance issues. After that, what, right? We have deep explainability and analytics for you to root cause analyze what is going wrong with your models, explain and evaluate your models, both on the training data set as well as what's happening in the production, to really get to the bottom of, okay, here is a problem. And you can layer that on with fairness, where essentially you are able to make sure whatever you're shipping are equitable models, right? So we are providing the entire package to actually build trustworthy AI solutions and also reduce your time to value for AI.
All right, there's a question on this person's super interested in issue tracking. How does that work? Can you give us an overview?
I would imagine this question is on alerts, right? When an alert happens.
Yes.
Okay, great. Sabina, you want to take that? Like, this is something that Sabina has been investing quite a bit in.
Yeah, absolutely. So we're actually, stay tuned for another webinar in a couple months. But yeah, we're revamping the entire issue tracking API story, NUI story. But to give you a little bit of a gist, and we kind of, hinted at it somewhere in the demo, users can go ahead and create what we call alert configurations or alert rules. And you can specify this, if you remember the donuts I showed, across performance alerts, data integrity alerts, data drift alerts, even traffic. Right? So you can set alerts on any of those, specify thresholds, time bins, and basically apply that to your different models. So as you publish production events, whether that's batch or real-time events, in that monitoring experience, you can actually see the data points that triggered those alerts. You can sign up for like PagerDuty or email alerts where we summarize that information back to you. And then once you're there, our monitoring chart will let you like debug further and see what exactly is causing those issues and where, let's say, drift is happening. Does that kind of answer your question, or anything you want to add, Sri?
No, I think, yeah, so we are building a complete, like our solution, our product already has an easier way to detect alerts when the alerts are fired, sending to the right platform so that you are alerted where you are. But we are adding a lot more functionality to it, like like what Sabina was mentioning on the homepage, and quickly get to the bottom of issues so that mean time to resolution is minimized.
All right. So a few more questions here. Is the model fairness pipeline tested and validated for conversation between a customer and support agents?
That's a great question. I would love to understand this particular use case a little bit more from the attendee who are asked this question, because it is all use case dependent, right? We have the fairness platform, which essentially helps you understand if there is bias that crept into your training data sets or your production data sets, and you can do deeper analysis. But talking conversations between customers and support agents means that we have to understand the particular use case a little bit more, so that then we can essentially figure out how this platform can be used by the support agents to translate into something that the customer understands, right? So I would love it if you reach out to us with this use case, and we can figure this out together.
Could I export Fiddler's explanations to our internal or end users?
Yeah, I guess I'll field that. This is one of my favorite use cases. So this is like the human in the loop use case. Like oftentimes you have somebody who may not be a data scientist who's ingesting machine learning predictions as part of their workflow. They might be a lending agent at a bank, or a fraud auditor in e-commerce, or a physician in a hospital making care decisions. Models are feeding them predictions. Yeah, so and this also gets to at least some of the integration and API questions. You certainly can use Fiddler as an explanation serving platform and feed that into external workflow for someone who's not a data scientist. Yeah, they do their job faster, they are less likely to miss important details, and it's better. They can leverage their domain expertise to communicate with model developers when something is inconsistent. It's a really excellent use of explainability in AI. Oh, I would also add that to the comment, the other question about integrating with other tools. We also provide in our explainability suite the ability for you to bring your own explainer that isn't part of the Fiddler collection. So there's a custom explanation pass-through that allows you to publish and serve explanations of your own type. Those can be included in user code, or they can leverage a lot of explainers that aren't formally implemented in our platform, but are available as libraries within the kind of user space wrapper code. So it's a powerful set of functionality.
Okay, there's 3 more minutes. We have a few more questions. I use Datadog for the infrastructure monitoring. Can I reuse it for model monitoring with Fiddler?
I imagine the question essentially is, hey, I'm using Datadog to interface for my DevOps infra monitoring. Could I integrate with Fiddler so that I can use Datadog as a singular view, right? I'm imagining that's the question. Yes, we already are able to integrate with Datadog to show the metrics on Datadog, so that if your other use cases in Datadog, you could pretty much integrate with Fiddler and have that as a single pane of glass for several of the scenarios. And if you want to go deeper into explainability and fairness and analytics, you could continue to use Fiddler for all the richer functionality.
Okay. Another question. We're building out, so they're starting out their ML tech stack. Can you integrate other solutions within the ML ecosystem? I think that's kind of a follow-up question to the previous one.
Yeah, so we integrate with any model framework. We are completely flexible. We integrate with any model framework. You can even easily bring in your SageMaker models, your TensorFlow, PyTorch, or or XGBoost, one of my favorites, or any data source. You can integrate with any data source. So we are pretty much a flexible platform that doesn't need you to change your pipelines as much.
All right. I think we're at time now, 11 p.m. Pacific. Thank you for joining us in this product webinar. And you'll receive a recording via email from us. And thank you for joining us for today's webinar. Thank you so much.